This presentation provides an overview of the AIM2020 Scene Relighting and Illumination Estimation Challenge. There are multiple different applications to scene relighting, both in computer vision and in computational photography. For example, domain adaptation or data normalization is very important when we have a model trained with fixed illumination settings and receive images from different settings. We can normalize them all into one fixed illumination, and then the network can perform better on that image. There's also data augmentation, which is in a sense the reverse process. Starting from one fixed illumination setting, we can generate many different images. There's also photo enhancement or photo montage. So scene relighting is very important because we can normalize all the different images used in the processing and then combine them together. The challenge competitions were based on the VIDIT dataset, which was a novel dataset designed for this workshop. It is made up of 390 virtual Unreal Engine scenes, each of 1024 by 1024 pixel resolution. Each scene is rendered using 5 different color temperatures and with 8 different light directions, which means that the light source was positioned north, northeast, or etc. This leads us to 40 different illumination settings, resulting in a total of 15,600 images in the dataset. The first competition track is the one-to-one relighting. The objective in this track is to transform an image between two fixed and known illumination settings, here from north 6500 to east 4500. The training dataset contains 300 different scenes with 1024 by 1024 resolution for each image. There are 45 images used in validation and 45 test samples, and the results are assessed using PSNR, SSIM, and LPIPS. The final ranking is based on MPS, the mean perceptual score, which is the average of SSIM and 1 minus LPIPS. We show on this slide the results of the teams who had a valid test submission. We show the MPS, the SSIM, LPIPS, and PSNR metrics. The MPS is the mean perceptual score, which is the average of SSIM and 1 minus LPIPS. We also show the runtime, platform, and GPU reported by the different teams. The first two CET teams were combined because their solutions had very large overlap. The top solution used the architecture based on MWCNN. The frequency domain allows for image-wide information learning, and the team uses the discrete wavelet transform to convert to the frequency domain. There were other solutions, for example, the coarse-to-fine relighting with channel attention that made use of high-level information, the norm relighting that makes use of white balancing normalization, or the residual learning on an hourglass network, and other solutions which are all detailed in the challenge report. The second challenge track was on illumination settings estimation. The objective of this track was to predict the light source position and the color temperature under which the image was rendered. The training dataset is made up of 300 scenes, again with 1024 by 1024 resolution, with each scene being rendered using 5 different color temperatures and 8 position angles for the light source. We use 45 validation and 45 test samples, with the results being assessed with the loss shown below. The loss measures the error in the angle prediction modulo 180 and in the color temperature prediction. And this loss is used for the final ranking. We show here the results of the different teams who had the valid submission for the test phase. The loss is shown on the first column, with the angle loss and the temperature loss also separately shown. So temperature loss is the squared error in prediction of the color temperature, and similarly for the angle loss is a squared error on the angle modulo 180. We also have the runtime, the platform, and the GPU that were reported by the participating teams. The top solution uses 2 different networks for the angle classification and the color temperature classification. And so the top solution was based on the ResNext architecture for the angle prediction and the ResNet 50 for the temperature prediction, both of which are pre-trained on the ImageNet. The other solutions had Illuminate ResNet that used RGB-UV histograms for the feature learning and white balance data augmentation as well. Also, there was a DenseNet that used selective blocks and other solutions, all detailed in the challenge report. The third track was any-to-any relighting. So the objective of this track was to transform an image from unknown illumination settings to those of a guide image that contains potentially different illumination settings. So the difference from track 1 is that we don't know the original settings that the input image might be in, and we also don't know the target settings. Those are given by a guide input image. Due to the complexity of this task, we reduced the resolution of the training and the test data to 512 by 512. Again, 300 images were used for training. The remaining 90, we had 45 pairs for validation and 45 for testing. When we say pairs, it's of course the input image that needs to be transformed as well as the guide. And the final output is assessed again with PSNR, SSIM, and LPIPs similar to track 1. And the final ranking is also based on the mean perceptual score, so the average between SSIM and 1 minus LPIPs. We show here the results of the different teams that had final submissions to the test phase of track 3. The same metrics as in track 1 are used and shown in the table above. The top solution uses a self-attention autoencoder with illumination settings estimation and manipulation that happens in the latent space, as shown in the figure on the bottom left. There are other solutions, like norm relighting that made use of white balancing normalization, or residual learning on an hourglass network with a target and prediction illumination mapping. This meant that this method predicts the illumination settings out of its own relit image and then matches them to illumination settings predicted from the guide image, which was a very creative approach to include in their method. And other solutions are all detailed in the challenge report. The limitations that we observed were mainly in tracks 1 and 3, and the difficulties that most participants had were in the shadow casting and in painting, which remain very challenging problems in our single light source setup. So you can see in some of the solutions on the right, these are taken out of track 1. The CET solution does a good job at getting the right illumination, at least the color temperature, which is very similar to the ground truth. Also the light source, you can see that the light source is brightest on the right side, but in painting the shadows, so basically shadow removal that is due to the shifted location of the light source, remains very, very challenging for all the different teams. In future work, we want to address the problem with geometry information, so using depth maps to be able to better cast shadows, because not only should the wrong shadows be removed, but there should also be new shadows being generated by the new position of the light source. So there will be a second edition of these challenges that plan to propose in NTIRE, which would be part of CVPR 2021. The novelty of the second edition is that it would involve depth maps to promote geometry-aware solutions and improve the shadow casting. The dataset used in the different challenges is already made public. You can find it on this GitHub repository. And if you want to repeat the similar tracks of the competition, the data, training data, as well as validation inputs, validation ground truth, and test inputs are provided. The test targets are kept private. And we also have some of the participating solutions that are also shared on this repository. And you are welcome to also add yours by doing a pull request on that repository. We lastly thank all the sponsors that made this workshop and the competitions possible. And we hope to see you soon in our following edition. Thank you.